Hello, everyone. This is Mark Anderson from Staddies Incorporated, here to talk to you about the do's and don'ts for screening process factors. This is an area that is quite interesting to me because as a chemical process development engineer, I did a lot of scale up and also plant process troubleshooting. Quite often, what the experts thought would be affecting the process wasn't wrong, but there were other factors and factors that interacted with the factors that they thought were really important. So having a good strategy of experimentation is really essential to being successful for plant process troubleshooting and process development. I'll go ahead and start my presentation now. As I'm starting the show, on your control panel, there's a control that looks like a hand. If you press that, then I know that you can hear me and you can see the presentation. All right, I'm seeing the hands coming up. Great. Thank goodness for the internet and go to webinar. Okay, so let's begin. As I said, my topic today is the do's and the don'ts for screening process factors. A lot of people get onto this idea of screening, but they use designs that are very low in resolution. And that's going to be one of the main things that I'm going to focus on here in my little presentation. I've got all the attendees on mute. If you put in chat, I may or may not get to it during the presentation, but I will take a look at it afterwards and hang on for a few minutes. Otherwise, jot down your questions and then follow up after the presentation by emailing mark@staddies.com. Now, this presentation will be recorded and posted on YouTube, and those of you watching on YouTube, feel free to send questions in to mark@staddies.com. Those of you that are attending live today can follow up afterwards at this website, 3wstaddies.com/webinars, and there you'll see a posting of the slides and also the link to the YouTube webinar. Just wait a couple of days to be sure that that comes through. So again, I'll just ask you to press the raise hand button if you're with me so far. All right, I'm looking through the list. It's quite impressive. At the very beginning, I've got Ad and Adu and Alan, and then it goes all the way through to the end of the alphabet, and I'm down to Sam D and some others. Okay, thanks again for attending, and let's talk about screening the do's and the don'ts. Okay, so what's in it for you? Sometimes we call this the WIFM, what's in it for me? In this webinar is how, if done properly, design of experiments, or DOE, provides huge process improvements via small screening studies. Let's do it. But why resolution 3, low resolution 2-level designs, the standard 2 to the K-P, or the very popular Plackett-Burmans designs, should be avoided? Don't. But if you do run a Plackett-Burman or a resolution 3 2-level design that's a standard 2 to the K-P, what can be done to follow up? It turns out that there is a technique called fold-over that adds a second block of runs that can set up a higher resolution that will be adequate for screening. And sometimes you're in such a hurry that you deploy these Plackett-Burmans and resolution 3 designs for a quick process fix. So while I don't recommend doing the resolution 3 and Plackett-Burmans, if you do, following up with the fold-over to de-alias them is quite a good thing to do. So we'll say do if you must. George Box, at a seminar I attended back in 1996 when he was teaching at Madison, Wisconsin, said running these Plackett-Burmans and resolution 3 designs is kind of like kicking the TV to make it work. Well, sometimes you really want that TV to work if you're anxious to watch something right now, or your plant process is in a bad state. But doing a follow-up is a way to kind of, get the best of both worlds. However, I really think choosing a resolution 4 or better design from the start, but actually resolution 4 is just right, like the Goldilocks chair, that's just right for the screening. And so we'll talk about that, and I'll give you some case studies. So consider that, do it right the first time with a proper screening resolution 4. So ultimately then, hopefully this will provide enlightenment on the fine line of reliable screening with a minimum number of experimental runs. So trying to get, just to the right point where you have enough runs to be able to resolve main effects, but you can quickly do many factors in a minimal number of runs. So here's a great strategy. I really think this is tried and true. It goes back to DuPont and their developments that followed the invention of response surface methods by George Box and a fellow named Wilson in 1951. Once this aspect got developed for the DOE strategy of being able to optimize with designs that had 3 or more levels, the standard design being a central composite design that is comprised of a factorial with the star points on the outside and a number of center points. Then we had the final part of a really good strategy that DuPont called SCO, which stands for screening, characterization, and optimization. And my focus is going to be on this first step, the screening. And one of the things that kind of surprised me, and it took me a while to figure this out, is that you don't include factors will affect the process. And that was something that never really occurred to me, but the advantage of that is that you can focus on previously unknown factors and very quickly, with a broad and shallow 2-level design, you can screen down to just a vital few factors and discard the trivial many. And quite often you end up with, maybe 20% of the factors that you didn't think were going to affect the process actually affecting the process. Well, then you can merge in, the known factors and then follow up with a more in-depth characterization. And at this point, we add in center points, which are really critical then for segueing if you see significant curvature and important curvature into these response surface methods. The second phase is where we're really going to focus on identifying 2-factor interactions. And so we end up in the first phase with kind of a medium resolution, let's call it a resolution 4 design, that'll be good for determining main effects. But we allow the 2-factor interactions to be somewhat muddled together because we know that following up with this first phase, we're going to do a more in-depth study. And we'll do either a resolution 5 or even a full 2-level at this point. And there's some other options that can be deployed for screening. In particular, there's a design called a definitive screening design that actually works pretty good. It's a minimum run design that will resolve main effects clearly. However, it requires 3 levels. And so that's a design that is not one of my favorites just because doing the 3 levels and also the temptation to move from a definitive screening design all the way through to an optimization and taking a shortcut worries me a bit, but definitely that's an option. So one of the things that precipitated me talking about screening was this common don't that came into our stat help, which we offer to our users. Stathelp@staties.com is something that any of our licensed users can address, with questions about their design of experiments or the results that they're getting using Staties software. Now, what happened here, and this is very common, this was a pharma process developer. They sent me these results, and it reminded me of how the inventor of statistics, Ronald Fisher, said back in the 30s that a statistician is more like a pathologist than a medical doctor. They can declare the patient dead, but they can't bring it back to life. And I really wish this pharma process developer had contacted our stathelp@staties.com before running this design, because what he did is he looked at 7 factors, such as time and temperature, things like that, that he figured would affect his product yield and purity. But what he chose was this option here, which is known as a saturated 2 to the k minus p design. 2 to the k minus p in this case is 2 to the 7. That's the k, which is 7 factors. And the -4 is the p, which is a fraction. which is 2 to the minus 4 or 1 over 2 to the 4 or 1/16th fraction. And right away you notice on our design builder with Design Expert or States 360, which includes all of the Design Expert features, is that this is a red design. And meantime, you see that there's some yellow options, like here's one just below, from the 8 runs going to 16 runs would progress into a perfect screening design. Even more ideal would be this minimum run screening design, which has got 8 factors. So even you could throw another factor in 16 runs and you would resolve main effects clear of 2-factor interactions. So the yellow designs, we label as screening. The red ones we say, are really good only for ruggedness testing, which is a topic I covered in an earlier webinar. If you think nothing is going to be significant, then maybe you would pick this design of 7 and 8. But if you're actually screening and you have some ideas that maybe 20% of these factors might be vital, then you really should progress up to this yellow zone. However, it was what it was, but then to compound the issues, this experimenter replicated this experiment. So now I'm thinking this is a really a waste of effort, because we're taking a bad design and we're copying it. It's kind of like taking a bad copy and copying that. If you're going to do 16 runs, you might as well start from the beginning by doing this resolution 4 medium yellow design that will resolve the main effects. And then one more thing, just to add more insult to injury, is that he did 1 center point. And actually, when you're doing the screening designs, you're better off not wasting time on center points just yet. Now, I have some issues with that. Sometimes I would go ahead and run center points, but I would never run just 1, because now you've got sample size 1 and any idea of any curvature in the center is going to be totally leveraged with only one center point. So I would recommend, if you are going to run center points, you run 4, at least 3, but 4 would be a good number. But I wouldn't run center points in a screening necessarily, especially if runs are dear. So to recap what happened here with this actual experimenter that sent this design in and wanted me to salvage it, is that doing only 1 center point is not effective. I would suggest doing none, which would be best for screening, or maybe doing 4 center points. But more so, if the design is meant for characterization of 2-factor interactions, then if that's the case, I would go to the resolution 5 or higher, which are either these green designs or the full factorials. Then run the center points for sure. Okay, so then, though even better yet would be at the very start, rather than doing a resolution 3 red ruggedness test design with 7 and 8, especially then replicating it to 16, this experimenter, I said, you would have been far better off going to the unreplicated yellow design for 7 factors at 16 runs. And in that case, you'd preserve the power that you would get from 2 replications. So what I'm going to do now is I'm going to start up States 360. Now remember, this is a more advanced package that came out fairly recently, as you may or may not be aware, but hopefully you know about this. States 360 is our flagship software nowadays, and it basically includes all of the features of Design Expert, as you see from this design tree on the left. The only thing is that we also now add to States 360 the space filling designs, such as Latin hypercube and optical distance. These are good for computer experiments, and particularly ones that generate deterministic results. Another big feature of States 360 is this Python script editor. And those of you that are adept with Python definitely want to go for the 360. But for the most part, and this particular user, the Design Expert works perfectly fine, and either of the packages will present this regular 2-level factorial design, and along the white diagonal are the full factorial designs. And then as you go up, once you get to 5 or more factors, for example, with 7 factors, you certainly would want to consider doing this fraction, 1/2 fraction, 1/4, and 1/8 might be actually the best choice of all to try to minimize the runs. But doing the 7 and 8 creates, really bad aliasing of main effects with 2-factor interactions, and you can see this in the alias screen. So if there are any things that interact, they're going to be confused with main effects. Now, replicating this, doesn't make any difference in terms of the resolution. However, if we go to one replicate and then go to the 7 and 16, we now have a design that's got a higher resolution, resolution 4. Main effects are aliased with 3 factors. That adds up to 4. And the 2's remain aliased with each other, but at least you have some chance of seeing that there might be interactions. There is a chance that interactions would cancel each other out, but it's pretty unlikely. So this really would be a good choice, the 7 and 16. So now doing the one center point doesn't really add anything, and I think that's kind of a waste of time to just do the one center point. So I thought what we would do now that we've viewed the aliases is look at the power calculation, and I'm going to put in a difference of 3 for the delta, and I'm going to put in 1.8 for the sigma, and let's go back and see what happens with the power. Okay, so let's start with one replication of 8, for example. And never mind the aliasing. Here's where we would put the names and the levels of the factors. That's good. And then in here, I'm suggesting that let's say that we looked at, in his case, it was a yield that he was measuring in percent. And let's just assume, I don't know this for a fact, but let's assume that it's 3.8. I'm sorry, 3 for the sigma, for the difference, delta, and 1.8 for the sigma. Okay, so that gives you a signal-noise ratio of 1.67. That's pretty good. But the power for only the 8 runs is only 50%. All right, so now let's go back and say, well, he might have realized that power was going to be low. I give the researcher credit for that. And we look at 2 replicates, and we'll see what the power does. Okay, that's good. The power is up to 87.2%. Now, as it turns out, putting the one center point in really does very little for any kind of power. And even we warn people not to put in one center point in the software, but disregarding that, I don't think there was much of a change. It might have been 87.4 and now it's 87.6. So the center point doesn't really help for power being at the middle of the space. It doesn't create leverage on the main effect estimates or the 2-factor interactions. So that doesn't really help us. Now let's go to the 7 and 16 and go back to 0 center points. See what happens with the power for that. Hang on a second. Okay, one replicate of this. That was too much, doing 2 of those. Then we might as well have gone to the next level. Okay, 83%. So you see where this kind of hits a sweet spot where we're able to get a decent power for 16 runs, which I highly recommend. If you can go 16 runs, that's always good. And yet we also get resolution. And all of that was, overlooked and lost, because the design was not done right the first time. So hopefully this makes sense. I'll just pause here for a second and just ask you if you're with me so far in terms of the idea, if you're going to do 16 runs, you might as well go with a higher resolution. Put your hands up if you're with me on that. I just want to make sure that, I'm on the right track here and doing something sensible. Okay, great. I'm getting a lot of positive feedback on that. Thank you. So to summarize then, doing the design originally for 16 runs with the higher resolution would have been the way to go with no center points. However, if we had done a design like this, which he had done, then there's a way out, and it's called a fold-over design, and I'll show you that. And we can actually take this resolution 3, and by adding a second block of opposite runs, which kind of mirrors the original one, we can build up to resolution 4. And so now you have a chance to salvage this. So going back to our design with, let's say, well, I'm going to be very literal here and say that he ran this two replicates with this one center point and just do exactly what this researcher did, ignoring this warning that one center point is not a good thing to do. And seeing that we do have decent power, which at least there's that, but now we know the resolution of this is very poor, and we can double check it using design evaluation. Any matrix we can look at using design evaluation, and we can see the aliases, after the fact. So seeing that, what we can do is using the design tools, we can augment with additional runs, and the program is smart enough to realize that what we really want to do at this point is this fold over, which doubles the number of runs to increase the resolution. And it's usually done when you have a low resolution, very highly fractional design, and you still wish to screen for important factors. And that's exactly what we want to do. So I go ahead and say yes, and now I'm going to do a complete fold over. That means all of these factors are going to go opposite of what they were in the original run. And I think maybe if I go in standard order, we might be able to see that in the first run in standard order, in this first block, it was minus for A, and now it's plus for A. In fact, if you look at the column minus, minus, plus, plus, all the way down, you see it now goes plus, plus, minus, minus. So actually every column goes opposite. Now in this case, we have a center point in here in the first block and a center in the second block. It's still not good, because with the block correction, you're still not getting much in the center. So I still wouldn't have run the center point. We also have, more runs than we need in the second block. And so the pattern minus, minus, plus, plus, minus, minus, and all the way down starts to repeat at some point. And so I would take the additional runs out and just run, half of the second block and not continue to replicate that. So we would have had to do a little bit of work to repair this, but we could have helped, this researcher do that. So deleting the duplications in the second block, I'm not going to bother to view the aliases, but if we were to take those out, that would have also shown the high resolution. But let's go ahead and look at the resolution now of this design. And so you notice that we have main effects now alias only with 3 factors. It's a 1 and 3 relationship, which is 4, and we have 2s with the 2s. So this would be much more effective. At least we would know if any main effects come out, they're almost certainly the main effects. Very unlikely that 3 factors would interact. And then possibly we would see some 2-factor interactions. And take it from me, if I would have taken, half of the second block of runs out, that resolution would have remained the same. So then a couple more points as a follow-up to this little wayward experiment designer is that if in doubt, it's always better to ask for stat help before doing your next DOE. A la Fisher's statement of being more like a pathologist, we can, tell you what killed the patient, but we can't bring it back to life once you've already done the experiment. But if you contact us beforehand, then we can help you get it right the first time. But, if you've gone ahead and run a design and it's not working out very well, contact us anyways, because maybe we can help you unravel it. And I promise you, we will be gentle. And then the last suggestion is, especially for those of you that have some budget for industrial R&D work that you're doing, is attend one of our modern DOE workshops, one of the public presentations, or if you have enough colleagues, contact our workshops team and set up a workshop, specifically for your team. Okay, here's another don't for screening, and this is really a pet peeve of mine, the Plackett-Burman. Now, I really like the Plackett-Burmans for ruggedness testing, and you'll see in my 2021 webinar, which is available for viewing via our website, and the references here, you can get these links from the posting of the slides. It's actually a very good design for just ruggedness testing, for example, a test method development, or any kind of process development that's being transferred to the field. And my favorite is actually the 12-run design. This can handle up to 11 factors. If you have fewer than 11, you just kind of fill in the empty spaces with what are called dummy factors. So it can accommodate quite a number of factors. You don't have to do all 11, but that's a pretty good number if you're just trying to see if your system is going to withstand conditions in the field. However, it really doesn't work too well for screening. And the funny thing is that when you go back into the internet and you type in screening and the word Plackett-Burman, you come up with hundreds of thousands of hits, including this one from the NIST Engineering Statistics Handbook that recommends Plackett-Burmans. It says they should be used for screening designs. However, they say that main effects are in general heavily confounded with two-factor interactions. So to me, this is what I call an oxymoron. It's a conflict. I don't get it. I mean, if main effects are heavily confounded with two-factor interactions, how is this going to work? Now, it turns out that if any factors interact, these designs really do not serve well for screening. There's a somewhat of an idea, though, that because of the designs being run in multiples of 4 and creating some interesting structures of aliasing that are partial aliasing, that somehow this might be helpful for using Plackett-Burmans for screening, but I disagree with that. So I'm going to show you an example, and I'm going to show you a kind of before and after from our tutorial data on filtration rate. I'm going to show it as is, which was a full factorial, fit the model, and then I'm using the model in a simulation and then rerunning this design as if it was a Plackett-Burman. And then we'll compare the results that we get. Now, STATI software does provide a very nice palette of Plackett-Burmans. And as I said, they're really good for screening. And if you insist on using, they're really good for ruggedness testing. If you insist on using them for screening, well, that's up to you. And there will be a way to resolve them using a foldover. And so we do want to let you do what you want to do. But what we've done is we've provided a palette of the 4-run option Plackett-Burmans, because the standard 2-level design will give you an 8-run design. So you might as well pick that. But then for the 12-run design, here we have the 12-run design and it shows 11 factors. It would be done in 12 runs. If you didn't have 11 factors, we would just fill these out with dummy factors. And then other options that we have here are 19 factors in 20 runs, 23 factors in 24 runs, and so forth and so on. But by this point, you're getting into too many factors and too many runs, and I probably wouldn't recommend that. So I kind of feel like maybe the 11 and 12 is the real ticket for ruggedness testing. And notice we do warn that there is an issue with the aliasing of this, and you can see it here. Every main effect is aliased with, I think, 45 other two-factor interactions. It's partially aliased, and this is where things get kind of interesting. So every main effect in this 12-run design for Plackett-Burman will be aliased, and it's plus or minus 1/3 of 45 two-factor interactions. Therefore, if you have one or more two-factor interactions that create a large effect, you may get lucky and maybe there aren't interactions, but they will get misapplied to multiple main effects. And I call this being smeared out. The main effects are going to get smeared out across, the two-factor interactions are going to get smeared out across multiple main effects. All right, so let's see what happens with the simulation. So I'm going to go back to my STATI software, which happens to be the 360, but it just as well could be Design Expert. And I am going to open up tutorial data for filtration rate. Now this is used for the 2-level factorial tutorial. It comes from Doug Montgomery's book, Design and Analysis of Experiments, which is published by John Wiley & Sons. And the wafer board manufacturer that he was working with had to quickly reduce the concentration of formaldehyde. And it was a huge success. The actual tutorial you can bring up, and it would be the 2-level factorial. And so this is actually the document that comes up, HTML, that describes this particular case. And you can see the factors that are studied, the levels from low to high, minus to plus, and it's all detailed here. Okay, so let's see what happens. First of all, I'll rebuild this so you can see how it was built. So this one has got 4 factors, and it's full factorial of 16 runs. We do have the screening option, which would be 8 runs, but I'm going to go to the screening with 12 runs, supposedly with Plackett-Burman, which in theory would be even better to have 12 runs. But the original design had 4 factors, here's where you enter in the names and the units. This design structure does allow for categoric factors, so we could put in one type of chemical versus another, but these happen to be all numeric. Now, the only issue I have with this design is I normally, if you're going to do a full factorial, would have suggested doing 4 center points. And this would have brought up the number of runs from 16 to 20. Of course, we would do some kind of power calculation. These are just default numbers here. But hopefully you would be able to see we're clear to this design. And if I show the space point type, you can see that there's some center points that I would have recommended. I probably would shift one of the center points, this one that's in run number 19. For example, I might make this number 7 and make number 7 number 19. So I'm kind of a perfectionist and I like having these center points spaced out. This would make a really nice characterization design. Well, let's assume that this was done, mainly for screening. Let's just see what would happen if I reopen this data. Of course, doing a full factorial is going to give us a lot more than just screening of main effects. And here's what happens. It turns out there's 2, very large interactions, AC and AD. You can see them on the Pareto chart here. Okay, and then as far as screening is concerned, we would say that we know that now that temperature, stir rate, and concentration are important, and pressure, fails, to make it through the screening. So in a sense, we could say this would screen out pressure. But it also, because it was a full factorial, characterizes the 2-factor interactions. And these are true. I mean, they're not aliased with anything because there's no aliasing. All right, so now the fun begins, because what I'm going to do is I'm going to open up a design that I created from the model. In fact, let's leave this up here, and what I'll do is I'll run another program, another instance of Statis 360, just so that I still have the other one in the background. Okay, so let's go back to this new opening of Statis 360, which, being I work for the company, I have an opportunity to open up multiple instances of the same software. And you might have that at your end if you have a multi-seat license, if people don't mind you hogging all the design experts or the Statis 360s. So let me find this reincarnation of this design as a Plackett-Burman. Okay, now we have the same factors, and we can see this in the summary. Temperature, pressure, concentration, stir rate, but now we've filled out with dummy factors, E, F, G, H, J, K, L. Those are not actual factors, but they're filling out the matrix. So we're showing these patterns over here, but we don't actually pay attention to that. And then over here is the data that's been collected. Now this is using the exact same model. So I literally took this coded equation, 70, I think I rounded to 70.1, 10.8, 4.9, and so forth. And I typed that into a Statis simulator, which is a tool that we have in the software. And I even added in the standard deviation of 4.4 to it. And then I ran the simulation, and these are the results that I got. So let's see what happens. Now keep in mind the aliasing, and we can reevaluate that after the fact. And again, notice the smearing out of every main effect with 45 2-factor interactions. So what's that going to do? Knowing that we have a couple of 2-factor interactions that are very active, what's going to happen? Well, it's not going to be good. So to start with, it's kind of consternating because this lineup is very flat. Whereas before we had this nice division of the trivial many at the near zero level on this half normal plot, and then minding the gap, we could see that there were some big effects off to the right. But now it's, kind of all muddled up. But anyways, why not pick one of these factors anyways? It turns out to be temperature. Well, that's right. So that worked. Now let's go to the next one. Uh-oh, that's factor E. That's not a factor. If we right click, we can see that E is aliased with all these 45 two-factor interactions. Guess what? One of those is the AC interaction, I think, and another one might be the AD. So I did a little bit of work on this trying to figure out what happened because it was a complete fail. So again, here's the model that I put into the simulation. Right? And so in theory, we should have seen not only A, but some of these other factors, particularly C and D. Now we realize that we're not going to see the AC and the AD, but the bad luck is that E turns out to be aliased with minus 1/3 of AC, which is minus 9.1. So you're taking a minus times a minus, and you're getting a plus 3. Then it's also aliased with 1/3 of AD, which is a plus of 1/3 times a plus of 8.3, and 1/3 of 8.3 added up to 1/3 of 9.1 gives you an appreciable, effect, it seems, for E, but it's actually false. So actually AC and AD are being smeared out on E. Oh, by the way, what happened to factor D? It turns out that the D main effect is undercut by aliasing with 1/3 of AC, and that creates a negative. And so there's a kind of a canceling out that occurs. So D doesn't appear and C doesn't appear. So only A is screened by the Plackett-Burman, and we miss C and D. We also lose the opportunity to see a potential interaction. Okay, so I'll just stop here for a minute, and I'm pressing the hands down for a moment, but do you see what I mean, that this Plackett-Burman design can be dangerous, particularly if you have interactions of things? If you can see that from this little demonstration, give me a hands up. All right, and I'm seeing some hands up, and maybe they're coming up a little bit more slowly. But think about that, and maybe do your own little pseudo experiments. You could actually do some simulations of your own if you have some DOEs that you've run, or you could use some of these textbook DOEs and check this out for yourself. So I really think it's kind of a misconception. Now, the nice thing is that we can actually fold this over. And so I'll show you that real quickly here. Let's close out one of these Staties 360s and go back to the other one that's got the Plackett-Burman. Okay, so now we can take this design and, using the same technique of augment design, augment with additional runs, we can fold this over. This again will double the number of runs. We're going to do a complete fold over. And then you can see that it's created a second block of runs, and these have all gone opposite from what they were before. And so where we went 35, 24, 35, 24, we're going 24, 35, 24, 35, and all the other ones are going opposite as well. Now this we can evaluate, and hopefully we'll see that we've improved the structure of this. This is calculating fraction of design space, which is a tool that is used for sizing response surface methods and so forth. Okay, so now the main effects are shown clear. They're actually not clear if I didn't ignore the three-factor interactions. Let's see. I'll cancel out of this FDS. Okay, so there's actually some aliasing of main effects with three-factor interactions, but that's essentially a resolution 4 now. And then the two-factor interactions remain aliased with multiple two-factor interactions. So it would be a little bit harder to work with this resolution 4 folded over Plackett-Burman than a 2 to the k-4 that would have clean aliasing of two-factor interactions. But nevertheless, this would succeed. And I think I made an actual simulation of this. Let me just check and see. Okay, yeah, I don't have this one. Actually, I don't have any data for it, but take it from me that if you took this Plackett-Burman and folded it over, it would resolve now the main effects, de-aliased. And we actually recommend this fold over for the ruggedness testing. And this is actually an ASTM standard E1169 ruggedness testing. So for the ruggedness testing, if we see an important effect, even if it's insignificant, certainly if we see a significant and important effect in ruggedness testing, then we would fold over the resolution 3 Plackett-Burman and try to figure out what caused the ruggedness test to fail. Now we could continue on with the second phase if we did fold over the Plackett-Burman, if we were trying to develop a process by doing a resolution 5 on the surviving screened factors. And at this stage, I would add center points. So that would be the next phase called characterization. However, I mean, what we really should be doing is doing it right the first time and starting with a resolution 4 design. And there's actually several options. I've showed you the resolution 4 regular 2-level, which is 2 to the k minus p design. So those are good choices, those yellow designs on our design builder. We also have a minimum run screen option, which is really handy as you get into 9 or more factors. So once you get to 9 factors, then you've got to go up to 32 with the 2 to the k minus p. So I would go to the minimum run screen option, which technically is 2 times 9 or 18. But because even one run might get botched, would throw it into a resolution 3. We recommend this minimum runs plus 2 option, which gives you a little extra, in case any of the design runs get botched. And then I mentioned the definitive screening design. I definitely question that. I see a lot of academic ideas that you can achieve a shortcut by this being a 3-level design all the way through to optimization. But I'm just kind of leery of taking that approach and skipping the step of characterization as a former process development chemical engineer. All right, so I'll finish up with this case study that is doing it right the first time, which is using a resolution 4 for screening, not using a resolution 3, 2 to the k minus p or a Plackett-Burman, but going with a resolution 4. And this is also another example from Doug Montgomery that's been slightly adapted, but it comes from his book, Design and Analysis of Experiments, and it's problem 8.26. I think I'm one version behind, at least on his new editions, and sometimes those numbers shift a little bit, but you should be able to find this if you've got the Montgomery book. So he had done quite a bit of work. It might have been after he went to Arizona State, with engineers that are working at fabs, which are making these silicone wafers. And in this particular study, they were looking at applying a photoresist, and they wanted to get a control over the thickness of that, being applied to a bare silicone wafer. And so I just got a little note, and this is a carryover from a class I was teaching this week on Zoom, that I was signed out of Zoom. So just to make sure you're still hearing me and seeing me, I do see an audience view that the screen should be showing, but just give me affirmation again that you're able to see this picture of this fab engineer pushing buttons on the control panel. Okay. So we have a nice little setup here, right? Because this is perfect. You can just press, this button or press that button, adjust this little parameter on the control panel. And pretty soon we've got an experiment that should be pretty easy to do in a randomized plan on the spin coder, changing spin speed from 1 RPM to another, the acceleration of that spin speed, the volume of the resist that's being applied, and cc's, how long you spin it for. Here's a categoric factor. So these 2 factors are categoric, which is fine. We can fit that into the 2-level experiment. And this one's kind of fun because either we leave the cover on or we take it off. And again, this came from the Montgomery experiment. So as we will see, this experiment did uncover not only some main effects, but also some potential interactions. And it turns out you can also resolve with a fold over, but you have to do what's called a semi-fold. The full fold over, surprisingly, doesn't work. So let's take a look at this. We have to be careful with any interactions that might show up because statties will just arbitrarily label these alias effects with the one that has the smallest degree coming first in alphabetical order. Because, you know, the columns actually line up perfectly and there's no way to resolve it. So the software will just arbitrarily label, and you have to be aware of that because sometimes you think the software has got some miracle tool that can de-alias, you know, things that are perfectly aliased, and that's not the case. So I'm going to go ahead and I've got my little instructions here that I'm going to follow. I'm going to open up a file called thickness. And this will be the original study that was created by Montgomery. All right, and so how did we set this up? We're using the same factors. You can see that this is picked as 6 factors and 16 runs as a yellow design. There's no center points. We look at the alias structure and see main effects are aliased with only 3-factor interactions, which is resolution 4. The 2-factor interactions will be aliased with each other, but that's fine because we just want to screen this and see if we've got, you know, a decent, we have the correct factors, and maybe we're holding aside some other factors according to the strategy. So we just want to know out of these 6 factors, you know, maybe a vital few of them that come through. So now we collect the results, which is thickness on average. And here's the selection over here. And of course, it's a textbook example, so we get this nice separation, spin speed, main effect, main effective acceleration, and so forth like that. Okay, so then we've got A, B, C, and E. It appears A, B, C, and E are the key things. But then we have this A-B interaction. Now, the interesting thing here is if we right-click this, we'll see that actually AB is aliased with CE. Now, here's where sometimes you can kind of make a guess at the interaction by figuring that it should be comprised of parents that are already in the model. But because A, B, and CE are totally aliased, and we also have the main parents of A, B, and C and E, there is a possibility that, although it seems more likely it really is AB, maybe it's actually CE. Now, the weird thing is that you would think that it really wouldn't matter as far as how the interaction looks, but because the parent terms differ, the interaction of AB looks like this, but if I substitute in for AB the equally likely CE interaction, it changes. And so I copied these out. And here they are on slide 15. And so on the left is, well, if it's the AB interaction, this is what it would look like. On the right, this would be the CE. And that one involves, you know, the effective volume depending on the vendor B versus vendor A, it changes. And the other interaction involves the spin speed effect changing depending on the acceleration. Now let's assume we talk to the experts in the spin coder and they look at this, and I bet you this would happen, and they would say, you know, I'm not really sure which it is. It really could be either one. Well, it turns out that we could do a semi-fold over, and we can resolve, and I'll show you how this would be done. It turns out that a full fold over would not work. So the temptation would be to take this and say, oh, you know, Mark just showed us this new thing. And that's like having a new hammer. Everything looks like a nail. So I'll just do a full fold over, even though it doesn't recommend it. In the software, it says to use a semi-fold over because it's too smart for its own good. But if we went ahead and did this, then we would still have the aliasing of the main effects with 3-factor, which is fine, but we still have this AB equals CE. So that isn't the right thing to do. So it turns out that if I would have paid more attention to what the program told me, if I had taken this original thickness matrix and done what the program said when I did augment with additional runs, then I would have done what's called a semi-fold. And it turns out if I pick out either A, B, C, or E, any one of those, it'll de-alias A, B, and CE. And so I could pick A. Now, the other thing is that with the semi-fold, we're going to take one of the factors and put it at just one level. So we thought maybe putting the exhaust cover on would be the way to go. And so here's this the design, and then over here we see that the cover is on throughout the 8 runs, and then the evaluation of the results should show us that this is now a resolution 4, at least for the A, B, and the CE. So AB is only aliased with 2 3-factor interactions, and C is only aliased with 2 3-factor interactions. Now, some of the interactions are still aliased with each other, but we're not worried about that. Okay, so that is called a semifold, and if you're interested in this, it's detailed in this presentation that I gave with our founding principal, Pat Whitcomb, and my long-term colleague going back to our days in process development at R&D for specialty chemical, how to save runs that reveal breakthrough interactions by doing only a semifolder on a medium resolution, which is a resolution 4 design. And this is posted, at this site. So if you haven't heard about this and you're thinking about doing screening designs, you might want to check into it, because this would be a nice way out if you see any interactions that are active. So to recap on the screening designs, don'ts and do's, I say don't include known factors. And this took me a while to understand it. At one point, I was arguing with Pat about this, because I said, well, what if the known factors interact, with the unknown factors? Then what? He said, well, you'll take care of that the second time through. I said, oh, okay. So we hold off till characterization, to worry about interactions of the known factors along with any vital that come out of the screening. Don't do a resolution 3 design, whether it's a standard 2 to the K minus P, which are the red designs, or the Plackett-Burman. I don't think those are good designs for screening. But do a resolution 4 to start with, or a minimum run screen. Those are the 2 that I think are the best. They just maintain 2 levels. It's simpler. And then if you see 2 factors emerge, 2-factor interactions, consider doing the foldover, the semi-foldover, not the foldover, but only half the number of runs, which is even better yet, which is called a semi-foldover. Okay, so that brings me to a close here on my presentation. What was in it for you was that you could see that if done properly, DOE can provide a huge process improvements with small screening studies, so do that. And why low resolution designs, such as the standard 2 to the K minus P red designs, or the Plackett-Burmans, which mirror the 2-factor interactions, and those are also resolution 3, should be avoided. Don't do those to start with. But if you do a resolution 3 standard or a Plackett-Burman, consider doing a full foldover. Okay, because that'll give you a quick process fix, to salvage the screening. So I'd say do if you must. And then, of course, doing it right the first time by choosing a resolution 4 design is really the way to go. And you can also semi-fold, which is better yet because it's only half the runs, to de-alias any 2 FIs. So that was kind of a bonus that I presented. So I hope that this provided enlightenment on the fine line of reliable screening with a minimum number of experimental runs. What do you think? Did I accomplish the mission? Looking for hands. Okay, Alvin, thank you. I'm not shy about asking for approval, so thank you for that, Eric, Gary, and a bunch of other people. Okay, now I do see some questions coming in, and so let me just wrap this up. And if any of you want to hang on, I generally try to wrap up within an hour, but I can stay a little bit longer and address questions. So let me just finish up by saying that if you're interested in learning more about this, aside from the references that I provided, pick up this book, DOE Simplified. It's a nice light paperback book, if I do say so myself, being the prime author of it. And this will cover, the concepts of screening, characterization, the discussion of Plackett-Burman, fold over. There might maybe some semi-fold over. I'd have to go back and look. And that would be a nice, reference for you. It's available from Amazon or any of the internet bookstores. And then I would highly recommend the Modern DOE for Process Optimization workshop that we do. It's either presented public or private. Nowadays, as you saw with the Zoom messages popping up during my presentation, it's done by Zoom at a distance over a 5-day period, 3.5 hours per session. And if it's a private presentation, if you have a bigger team, then you can tailor it a little bit more and have it, set up over a period of time. I just finished up Tuesday a 5-session Modern DOE for process optimization for a company based in Finland and Germany, and they did it every week. So every week on Tuesday morning at 7 in the morning, I got up because they're 8 hours later in Finland, and we just finished it up on Tuesday. But I think maybe rather than spreading it out over 5 weeks for a private presentation, I kind of like doing it maybe two days 1 week and 3 days the next week or something like that. But you can contact our workshops team and get that figured out. So that's it. If you want to stay on for just a minute, I'm going to click the chat window and see if I can find some things. But those of you that want to take off, feel free. And I certainly would like to thank you for attending this presentation. And likewise for anybody that's attending the presentation, on the YouTube. Thank you for watching. Thank you for listening. And do get back to me, mark@staties.com, if you have any questions. Okay, so let me just click questions. We'll pop that out. And going to the first one that came in from Eric was, when you are evaluating aliasing, what are you looking for? When demonstrating the resolution 3 fold over, the number of runs is doubled, regardless of whether a factor has been found significant or not after the resolution 3 execution. Wouldn't it be more efficient to use an optimal design augmentation? That was Sam D. I think I was kind of pushing through into a second question there. But yeah, what I'm looking for, Eric, to start with is I'm looking at main effects and two-factor interactions, and I'm concerned about only those main effects and two-factor interactions, because I really think if I've done a good job as a chemical engineer developing a study and giving a certain focus on it, that there probably won't be three-factor interactions, that'll be active or needed for modeling. So my focus will be completely on main effects and two-factor interactions. Now for a screening, I'm going to focus on main effects, and I want to make sure that they're aliased only with three-factor interactions. I don't want them aliased either in whole or part, which happens with Plackett-Burman, with any two-factor interactions, because especially as a chemical engineer, I'm very sensitive to the potential of two-factor interactions, being possible. And then in terms of the resolution 3 fold over, they will double the runs, and some of the columns are factors that don't appear to be significant. However, we don't know that because of the aliasing of main effects with two-factor interactions. And it's possible to have interactions that don't have either parent present, even without the smearing situation we have at the Plackett-Burman. So I have actually tried, the technique of deleting some of the factors and then folding over, and I don't recommend it. I didn't have a good experience with that. Similarly, yes, you could use the optimal design augmentation. And I didn't really demonstrate that, but you can basically take any matrix. Under design tools, we also have the option of optimal. We have factorial optimal. You could even take this semifold that I created and now turn that into an RSM design through optimal design augmentation. However, once we go to the optimal augmentation, then the computer kind of takes over and does some funny things. So I definitely like the optimal design augmentation for certain situations, but if we can use a standard template approach like a complete fold over for resolution 3 or a semifold for resolution 4, I still kind of prefer that. And then Eric asks about the type of design used by Staties for mixture design screening. And actually, it turns out that we have a tool that can be used for screening. straight away for the mixture design. And so if we were to completely start over with mixtures, the same strategy of screening can apply. And I definitely promote that. And I've always thought the chemists were too quick to grab off, only a handful of things off the shelf for surfactants or whatever, thickeners. And they just said, oh, I'll grab a little bit of this, a little bit of that. And here we go, we start mixing it up. And I always wondered, well, why not consider doing a screening? So for 6 or more components, we offer these screenings. And so it's right there on the design, it says screening. And the number of runs is then going to be minimized, and we're just going to be looking at linear blending effects. And there's a couple of different options here. We have a bare minimum for 10 for a simplex screening. I probably would add these axial check blends to it. So that would be one of the options. The program can detect if you have a non-simplex. We can just enter in a restriction on the first factor, and it'll kick this over to what's called an optimal mixture screening. And in this case, we've gone from 10 vertices up to 18 vertices. And this one just says do all 18 vertices. But as you get into more and more restrictions and more components, then the number of vertices will start to explode. Like here's one we're doing only 34 of the 47 vertices and so forth. So that's called a mixture screening, and it's the same strategy that we've applied for the process factor screening. Okay, let's see, do we have, okay, we covered that, and I think maybe we've got everything. So I think what I'll do is I'll wrap up at this point. And yes, Ross says, thank you, Mark, have a great day. So I think that's it then. Thank you for everybody that hung in here right to the very end. I do appreciate it. And if I didn't answer your questions, as thoroughly as you'd like, for example, SOMD, feel free to get back to mark@stades.com. And I look forward to hearing from you. And thanks again for attending. Okay, take care now. Bye-bye.